Well, welcome to construction equipment, and today we're going to talk about a new topic after learning about equipment economics and after learning about the cost of equipment and after learning about the properties of soil. Now we're going to start talking about individual pieces of equipment, their uses, their production rates, their cycle times, and so on and so forth. The first group of equipment that we're going to be dealing with is what's called hydraulic excavators. So what are they? An excavator is a power-driven digging machine. The primary use is to excavate soil, to dig. Major types include hydraulic excavators, shovels, draglines, hose or backhoes, and clamshells. Other equipment such as dozers, bulldozers, loaders, scrapers may also be used as excavators, although that would not be the optimum or the ideal use for these equipment. But again, if you own this equipment and it's available on site and you need to do some excavation, this equipment can do that as well. Not as efficiently as the first group, but it still can do it. Here are some examples, or some pictures. This is a drag line. So as you can see, the bucket is connected to a crane and it uses its own weight to penetrate through the soil. This line is brought back, it's pulled back so that the drag line can scoop the soil and then it's dumped somewhere else. Here's a backhoe where we have the bucket facing backwards attached to an articulated hydraulic arm, and it's used for excavation. Here's a clamshell, and as you see, the bucket for the clamshell is used primarily for relatively loose soil. It's also attached to a crane similar to the drag line, and it uses its own weight to penetrate through the soil, and then the clamshell is closed and the soil is scooped. The generic equation for an excavator is estimated through the equation: production per hour is equal to the volume per cycle times the number of cycles per hour. Volume per cycle is going to be affected primarily by the bucket size and some additional factors, as we're going to see, like the fill factor and the load factor and so on. Cycles per hour determine how many cycles can we achieve. The cycle is going to include excavating, turning, dumping, turning back, and getting ready for another cycle of excavation. This is called a cycle. So it's going to take a few seconds. So how many cycles can we achieve per hour? So the volume per cycle times the cycles per hour is going to give us the production rate per hour. The volume per cycle depends on the rated bucket capacity and the bucket fill factor. Some soils can be heaped inside the bucket, so actually the bucket capacity is going to exceed the actual size of the bucket, and in some other cases it's going to be less than that, especially if we have lots of voids between the particles. Like if we are filling a bucket with rocks, it's going to have a lot of voids between the rock particles. So in this case, the rated capacity is going to be, or the actual capacity is going to be less than the rated capacity of the bucket. Here are some examples. So for a backhoe or a shovel using a cable, it's going to be the struck volume, and if it's hydraulic, it's going to be a heaped volume at a 1-to-1 angle of repose, so 45 degrees. For a clamshell, it's going to be the plate line or the water line volume. For a drag line, it's going to be 90% of the struck volume of the drag line itself, the bucket. And for a loader, it's going to be a heaped volume at a 2-to-1 angle of repose. 2 rise over run, the slope is measured as rise over run, so 2 vertical, 1 horizontal angle of repose. So again, this is going to carry much more than the actual capacity of that bucket. Now the material fill factor or the bucket fill factor, different types of soils have different fill factors. So if it's common earth or loam, it's going to be very low amount of voids between the particles. Therefore the fill factor is going to be anywhere between 0.8 and 1.1. 1.1 means it exceeds the capacity, is going to be some heaping. For sand and gravel, it's going to be anywhere between 0.9 and 1.0. For hard clay, it's going to be 0.65 to 0.95. It's going to be lumped into larger particles. For wet clay, it's going to be anywhere between 0.5 and 0.9. Rock, well blasted, relatively graded, is going to be 0.7 to 0.9. And rock poorly blasted is going to be 0.4 to 0.7. So we're going to use only about half of the capacity of that bucket. Here we have an example. Estimate the hourly production for a loader with a bucket heaped capacity of 5 cubic yards. The soil is sand, and the load factor is basically to convert from loose to bank volume, because that soil filling the scoop or filling the bucket is going to be in its loose condition. So if we want to convert it and get the production in bank cubic yards per hour, we need to convert to bank volume. That load factor is 0.8. The cycle time for the loader is 1 minute and 30 seconds, which is 90 seconds, and the job efficiency is 80%. So let's see how we're going to solve this. First of all, the bucket load is going to be equal to the fill factor times the bucket heaped capacity. The fill factor for that type of soil, based on this equation, this table here, we mentioned that it's going to be sand. So for sand, it's going to be around 0.9 to 1.0. We can choose either one or any range in between, an average. So we're going to take, in this case, 0.9 times the bucket capacity, which is 5, which means we're going to have soil volume inside the bucket of 4.5 loose cubic yards. Then we need to convert these loose cubic yards into bank cubic yards. So we're going to multiply by the load factor. So that's going to reduce the volume. Therefore, each bucket is going to carry 3.6 bank cubic yards for each cycle. Number of cycles per hour is going to be 1 hour, which is 60 minutes, divided by the cycle time. Now the cycle time was given into minutes and seconds, so we need to make sure that we are using the same unit. So 60 divided by 1.5, which is going to give us 40 cycles per hour. That is with the assumption that we're going to use 60 minutes per hour as production. But this is not always true. We're going to have to look at the efficiency. The efficiency was given to us as 0.8 or 80%. Therefore, the volume, the total hourly production, is going to be the volume per cycle times the number of cycles per hour times the efficiency, and that gives a total production of 115.2 bank cubic yards per hour. Again, here's the table that we used to get the factor for the sand. The hydraulic excavator, also called hydraulic hoe or hydraulic excavator backhoe, depending on the way the bucket is facing. If it's facing forward, it's a hoe or a shovel. If it's facing backward, it's a backhoe. It digs by pulling the dipper back towards the machine. So there's going to be a hydraulic force pushing that bucket into the soil and then pulling it to get out of the soil with a breakout force to take the soil and to be scooped away. When the dipper is filled, it's curled up to reduce the spillage through the hydraulic arm of the equipment. And that's basically what it looks like. So here's the articulated hydraulic arm with pistons. And here's the digger or the bucket or the dipper. So it has some teeth at the edge to help loosen and break the soil. And once it's full, it's going to be tilted upwards to avoid or to reduce the spillage. It's used for trenching work, as it can also lay pipes, pull trench shields or sheet piles, and backfill the trench after the operation of laying the pipes is complete. The dipping width of the bucket should match the trench width to maximize production. So if we're going to use, for example, the width of the bucket is 3 feet, then the width of the trench should be around that. These buckets are movable. We can exchange these buckets and change the bucket size depending on the operation that we're going to be using it for. Telescoping booms may replace articulated booms. So instead of the articulation, we may have telescoping booms to extend the reach of that hydraulic excavator. The generic equation for estimating the excavator production is going to be pretty much the same thing, by the way, which is number of cycles per hour times the volume per cycle. But here we are basically adding some other factors that affect the production rate. So it's equal to C times S times V times B times E. Let's look at what each one of these means. C is the number of cycles per hour. S is the swing depth factor. Now imagine the cycle is going to include digging, swinging, dumping, swinging again, and starting to dig. The wider that angle of swing, the slower the operation is going to be, because you have to move a farther distance. Therefore, if that angle of swing is relatively narrow, that's going to expedite the excavation, which means reducing the cycle time, which means more cycles per hour, which means more production per hour. V is the heaped bucket volume. B is the bucket fill factor, which we have seen depending on the type of soil. And E is the job efficiency, which is how many productive minutes per hour can you get out of this piece of equipment. We have some effect from the job conditions. Depending on the job conditions, we can have either excellent job conditions, above average, average, below average, and severe. And for different sizes of buckets, we can have estimated cycle times. So for example, the excellent conditions are characterized as easy digging. We're digging through easy soil to break into. Unpacked earth, sand, ditch cleaning, etc. Digging to less than 40% of the machine's maximum digging depth. So the arm is not going to be extended to the maximum. And the swing angle is less than 30 degrees. Again, the amount of swing is relatively limited. You dump into a spoil pile, so you don't have to maneuver and to adjust to dump into a truck. No obstructions. You can see the dumping area, you can see the digging area, so that's going to be excellent conditions. For a less than a 1 cubic yard bucket, the cycle time is going to be about 13 seconds. 1 to 2 cubic yard bucket is going to be about 15. 2 to 3 cubic yards is going to be 16, and so on. The larger the bucket, of course, the longer the cycle time. Above average conditions are characterized as medium digging. Now it's not as easy as the previous one, but packed earth, relatively more consolidated and compacted. Dry clay, soil with less than 25% rock content. Now the depth, instead of being 40%, is going to increase to about 50%, so more reaching out with the arm. And the swing angles less than 60 degrees. So still, here in the first case we had 30 degrees, now we have about 60 degrees. It's still large dump target, so it could be a large truck or an open area, and few obstructions. As you can see, that's going to extend the cycle time by about 2 seconds. 2 out of 13, that's about almost 1/7, so almost 14% reduction. And so on. If we keep going down, we're going to see that the average conditions, for example, more hard-packed soil, depth even more, 70%, and the angle of swing up to 90 degrees, and loading into trucks. So you have to spot and you have to adjust, you have to maneuver, which again is going to slow down the operation. Up to when we reach the severe conditions, we have digging through tough and hard soil, depth over 90% of the maximum digging depth, so we are almost extended to the maximum, and a swing angle of over 120 degrees. So basically we are moving more than 90 degrees. It's basically almost facing backward. And it's a small dump target requiring maximum reach. So you have to maneuver to make sure that you don't spill that soil out of the dump truck. So it requires additional maneuvering. Now comparing between the excellent job conditions and the severe conditions, we find that we have here, for example, a difference of 8 seconds. 8 out of 13, that's almost 60%, which means that the production is going to be reduced considerably. Shovels, similar to the backhoe, but in this case it's going to be facing forward. The bucket is going to be facing forward. It's going to use 2 kinds of forces to break down the soil. Is going to have something called crowding force, which moves downwards, and then breakout force, which is going to lift that soil and dump it into the truck. So dig with a combination of crowding or down force and breakout or forward forces. It has a limited ability to dig below the track level, because again it's going to be a risk of over tipping forward. So we're going to try to avoid that. The shovel production, like the backhoe, is going to be exactly the same. C times S times V times B times E. And the production is mainly affected by the swing angle and the lost time during the production cycle, depending on the type of soil and the different job conditions, as we have seen in the previous table. The angle of swing between digging and dumping should be kept to a minimum to improve production. As we have seen, again, difference between 30 degrees and 120 degrees. So looking at an example here, for example, other factors to improve the production: having a level floor of cut, that's going to help with the stability. Moving frequently to be closer to the working face instead of extending the arm, moving on the tracks to get closer. Keeping digger teeth sharp, which is going to help with the crowding force. And better training for the operator. A skilled operator can definitely achieve more than an unskilled operator. So the ideal production is going to be equal to the bucket capacity times the fill factor divided by the ideal cycle time. That's going to give us the ideal production in, again, bank cubic yards per hour. And here's some, again, fill factors for moist loam or sandy clay: 1 to 1.1, sand and gravel 0.95 to 1.1, and so on. Now, based on the ideal shovel productivity in bank cubic yards per hour, this is sort of the theoretical production rate as given in the manual of that piece of equipment for different types of soils, for different bucket capacities. So, for example, for tough clay and a 1.5 cubic yard bucket is going to be tough clay, and 1.5, that's going to give us 210 bank cubic yards per hour. Again, this is the ideal production, not the actual production. Therefore, the ideal production can be obtained in one of two ways: either through a table like this or through an equation like this one, with the bucket capacity times fill factor divided by the ideal cycle time. The angle of swing is going to give us a modifying factor, with the 1.0 being represented by 90 degrees and 100% of the optimum depth. We're going to see that in an example in just a minute. If you dig less than the optimum depth or much more than the optimal depth, that's going to affect the production. If the angle of swing increases or decreases, again, that's going to affect the production. Job conditions, we have both job conditions and management conditions. Management conditions, basically something like having a good operator, a good observer, a good superintendent, good monitoring of the operation. You have the trucks lined up very close to where the soil is going to be dumped, so that the shovel doesn't have to move much. Job conditions, depending on how graded the site is, if you don't have too many obstacles, the equipment is in good condition, and so on. These are things that also we can't control. So we have another modifying factor based on the management conditions and the job conditions. For good job conditions, good management conditions, we get, for example, a factor of 75%. Let's now look at another example. A contractor has a project to excavate an apartment complex and must construct a 3-foot compacted fill to support a parking garage. The borrow site, where we're going to be borrowing the soil, is 3 miles from the construction site. So there's going to be a shovel over there, or a backhoe, or whatever piece of equipment, and that's going to dump into trucks, and the trucks are going to bring that soil to the site for utilization. The borrow site is 3 miles from the construction site, and 10 cubic yard dump trucks will be used to haul the needed fill. A 2 cubic yard shovel will be used to load the dump trucks. The material is tough, dry clay with a swell factor of 35%. The height of the cut at the borrow site is 11.6 feet, and the angle of swing of the shovel is 150 degrees. So estimate the ideal production using the table and using the equation. We're going to do that. And then estimate the actual production for good job and management conditions. The optimum digging depth of the shovel is 9.8 feet. This is the optimum, and this is the actual. So let's see this equation, this problem. From the table, we have two cubic yards for the size of the bucket. It's a tough clay, so using these is going to give us about 265 bank cubic yards per hour as our production rate. Or we can estimate the production using the equation, which is going to be more conservative. The fill factor from the table is 0.85 for that type of soil, which is an average between 0.8 and 0.9. The cycle time from the table again is about 21 seconds. Again, that's an average because for the 1 to 2 cubic yards is 20 seconds. For the 2 to 3 cubic yards is 22 seconds. What we have is exactly 2 cubic yards, so it's going to be anywhere in between, which is about 21 seconds. Therefore, the production is going to be the bucket capacity times the fill factor divided by the ideal cycle time. Now, the cycle time is given in seconds, and the production that we require is in hours, so we have to accommodate for that factor, which is 3600 seconds per hour. So it's 2, the bucket size, times 0.85 times 3600 divided by the cycle time times 1.35, which takes into consideration the swell factor, the 35% swell factor, to convert from loose cubic yards to bank cubic yards. Now, to get the actual, all of these were the ideal productions. So we had an ideal production of anywhere between 265 based on the table or 215 based on the equation. Now the actual production is going to be based on the modifying factors. The percent of optimum depth, the optimum depth was 9.8, the actual depth is 11.6, which represents 118 or almost 120% of the optimum depth. So using the percent optimum depth of 120% and an angle of swing that was given 150 degrees, we're going to find that the factor is going to be from the table here. 120% and 150 degrees gives us a modifying factor of 77% or 0.77. For good operating and job management conditions, the factor is 0.75 from this table here. Therefore, the actual production is going to be the ideal production, 265 times 0.77, the factor due to the optimum depth of cut and the swing angle, times 75%, the factor due to the job and management conditions, which gives a production of 153 bank cubic yards per hour. This is the actual production rate. Another piece of equipment is a dragline, which is a versatile machine with longest reach for digging and dumping. It's again mounted on a long boom of a crane. It's best used for soft to medium hard material. Sand is fine, gravel is fine, clay, relatively loose clay is fine. The bucket teeth and weight produce digging action as the dragline pulls the bucket back across the ground surface. So it's going to rely again on its own weight and the gravity, the pull of gravity, to penetrate the soil, and then we're going to drag it. We're going to pull the line to drag that soil and dump it away. The higher the point of attachment, the better penetration, again because you're going to have a higher penetration force due to the gravity and the weight of the bucket. As you can see, it has some teeth at the edge to help cut through the soil, and it's attached to that boom of the crane, and the drag cable is going to be used to drag that bucket once it's full. For the expected production of the drag line is going to be ideal output from the tables times swing depth factor times efficiency. Pretty much the same equation that we've had for the other pieces of equipment. Most efficient digging area is located within 15 degree angles forward and back of a vertical line through the boom point. So basically 15 degrees to this side and 15 degrees to the other side from the vertical line through the suspension point here. Deep cuts should be excavated in layers with a thickness as close to the optimum depth of cut as possible to increase the production rate, to improve the production. So here, for example, we have again with the optimum depth of cut of various sizes of dragline buckets. So here is going to give us, for different types of soil, what would be the optimum depth of cut for a 3/4 cubic yard, for 1¼ cubic yards, and so on. And also here we have the operating factors, the job conditions, and the management conditions, exactly the same table as we have seen before. And then we have also the dragline productivity correction factor based on the percentage of the optimum depth of cut and the angle of swing, as we have seen with the shovel, and ideal productivity based on the bucket size in bank cubic yards per hour. Let's look at an example. A contractor has a project to construct a large parking lot for a shopping center. The contractor decided to use a crawler dragline, which means it's going to be on tracks, with 1 3/4 cubic yard bucket to excavate a large drainage ditch to collect and remove storm water runoff. The excavated soil is common earth, and the average depth of cut is 7.6 feet. The excavated material will be loaded in dump trucks for removal from site. The angle of swing is 120 degrees. Job conditions are good, and management conditions are excellent. So it's not good and good. Job conditions good, management conditions excellent. What is the estimated dragline productivity in bank cubic yards per hour? And then we're going to add a couple of other layers. If the volume to be removed is 3,200 bank cubic yards, and the rental cost per day for that dragline is $1,800, how long would the operation take, and how much will it cost? So now we are also looking at durations and cost estimating for that piece of equipment. So from the table, the ideal production for 1 3/4 bank cubic yard bucket and common earth is 210 bank cubic yards per hour. We're just going to look at the table. The optimum depth of cut is 9.5 feet. The percent of the optimum depth of cut is, because the actual depth is 7.6, so it's 7.6 times 100% divided by 9.5, which gives 80%. Now using the 80% factor with 120 degrees, the angle of swing, gives us a modification factor of 0.9. For good job and excellent management conditions, the factor is going to be 0.78. Therefore, the actual dragline production is going to be the ideal, 210, times the factor due to the swing angle and the depth of cut, times the other factor due to the job and management conditions, which gives 147.42 bank cubic yards per hour. The total volume that needs to be excavated is 3,200 bank cubic yards. So dividing that by the production per hour is going to give us 21.7 hours, which is basically assuming 8 hours of work per day is going to be almost 3 days. We're not going to pay for a fraction of a day, so we're going to pay for the third day, whole day. Therefore, the cost of operation is going to be 3 days times $1,800 per day, which gives $5,400. That's the cost of that operation. Another piece of equipment similar to the dragline is going to be the clamshell. So it's going to be the same machine, but the attachment at the edge of the boom of the crane is going to be different. In this case, it's going to be a dragline. It's capable of digging at higher depths. That's one of the benefits of the clamshell. It lacks positive digging action and lateral control of the shovel or the backhoe. Again, positive digging, which means the articulated hydraulic arm is going to give that hydraulic force, that crowding force, but in this case it's going to rely, like the drag line, on its own weight and on gravity. It's used for excavating vertical shafts and footings for foundations. So this is what it looks like. And as you can see, we have here the lines that are used to open and close that clamshell, which has some teeth, again, to cut through the soil as possible. It's also used sometimes for grains and in marine operations and so on. The production is based on the equation, same generic equation, volume per cycle times cycles per hour. The maximum load should be limited to 80% of safe lifting capacity for rubber-tired equipment and 90% for crawler mounted equipment. This is a relative factor of safety, just to make sure that we're not going to have any over tipping or any stability issues with the equipment. And again, here we have a table that shows the different cranes and at the different boom lengths what's going to be the operating radius and what's going to be the total load that it can carry at the tip of that boom. And this shows basically the capacity of the clamshell bucket itself. The rated capacity is equal to VS, which is this bottom half, plus VE, the top half, which is the heaping, minus VM, which is at the joint where it opens and closes the clamshell. And here it shows again the different weights, because we can have either a general purpose bucket, a heavy duty bucket, or a light duty bucket. Each one of them is going to have a different weight on its own for the different rated capacities and different sizes of these buckets. To improve the clamshell production, we're going to have the dumping radius the same as the digging radius, so the boom is going to rotate and is going to dump at the same distance where it's digging from, keeping the machine level to avoid swinging uphill or downhill, because again, swinging uphill or downhill is going to affect stability and it's going to affect the effective length of the boom of the crane. So again, with the larger angle of swing, we're going to have different correction factors. The lower the angle, the better. The higher the angle, the lower the production. And again, for different types of soils, we are going to have different production rates for the different sizes of the buckets. Let's look at an example here as well. A contractor has decided to use a 2 cubic yard clamshell mounted on a crawler crane to excavate for the foundations of 3 concrete piers for a highway bridge. The excavated material will be dumped in stockpiles for later use in backfilling. The material is common earth, and the average angle of swing is 120 degrees. Job and management conditions are good. What is the estimated productivity of the clamshell in bank cubic yards per hour? So here we're going to look at the table. The bucket size is 2 cubic yards. We are digging into common earth. So 2 cubic yards with common earth gives us 160 bank cubic yards per hour. Now the factor due to the swing angle, we have a swing angle of 120 degrees, which is a factor of 0.91. Therefore, it's going to reduce our production. Now the factor due to good job and management conditions is 0.75 from the table that we have seen before. Therefore, the productivity, the actual production, is going to be ideal times the correction factor 1 times the efficiency or correction factor 2, and that gives 109 bank cubic yards per hour. Now I hope that would be a good introduction to the detailed discussions about different pieces of equipment. So we have learned about the cycle time, we learned how to use the different tables and the different correction factors. The equation is always the same, number of cycles per hour times the volume per cycle, and there are some factors that affect that volume per cycle and the number of cycles per hour. We have to include these correction factors to obtain the actual production from the ideal production from the tables that are given to us. I'll see you later on in another lecture. Bye-bye.